Right. Appreciate everyone jumping on. Looks like we've gotten back some of the people that I accidentally kicked off. Again, apologies if you were on this webinar a few minutes early. When I went to start everything, I had a little technical glitch and ended up accidentally ending the webinar and then restarting it. So I do apologize if you got kicked off. That was 100% my fault. I will try not to do that again until the end of the webinar. So what we're going to go through and do today is we're going to talk about, I believe, what Chad was sending out. The phrasing was RF video transport, RF video transportation. So what we're going to do today is focus on kind of like the design and a little bit of testing and implementation of a TV system, a coaxial-based TV system. And then we'll also obviously cover what our traditional Z-band infrastructure looks like in this. And I will spend a little bit of time on head ends and that kind of stuff. I make an attempt not to talk about head ends in this particular webinar because if you've been on these throughout the course of the year, you'll know that I talk about head ends a lot. So there's plenty of additional content that is head end related if that is the route that you want to go. So coax system design. There's two basic types. There's more than that, but you can kind of parse them all down into two basic types, which is the home run, which means everything's coming back from a single location, and the trunk and tap, which means we have a single location and a main line. Used to be hard line coax, RG59, half inch, whatever it is that you want to call it. The half inch coax is the hard line running up the riser and then tapping off in each IDF. And my personal favorite, which is the, hey man, I just need a television. And so I went to Best Buy and jumped up into the ceiling and made a few cuts and did my thing. If you have happened to catch me at any of the Big C regional ICT shows doing this presentation, you'd be a little bit familiar with this one. Some of these slides are going to be the same as a Big C ICT that I did. I think it was last fall. I think it was late last fall. So as we get into this, if you recognize a couple of slides, it just means you've seen them in a Big C presentation before. So the home run coax design is exactly what it talks about. Everything comes back to a central location. This one is super common in, think of like hospitality, small to medium size hotels. Everything comes back to a single TR, and then there's just a home run coax that goes out to each room or to each television. The fantastic part about that and what makes that nice and why people implement it. This is super easy to do, right? All you're doing is putting everything in, pulling a coax back to a single TR. We're not worrying about balancing a backbone infrastructure. We're not worrying about all kinds of different, calculations for amps, tap splitters, and everything else that are in the ceiling. You are pulling everything back to a single location, to breadboard on the wall, to a series of taps within whatever your telecom room or IDF is, and everything's working that way. The reason that it works out really, really well, and we'll get into it a little bit later when we're talking about loss calculations and some of those types of things, is because in a lot of these small to medium size hospitality environments, you're talking 30, 50, 75, 100 televisions across one or two floors. So your distances run aren't that far. Your distances are 100 feet, 200 feet, 400 feet. And if that's really kind of the max length that you're talking about running when you're designing a coax system, you don't need that much power to get that out that far. And with the loss over per 100 feet on RG6 and RG11, really a couple of 35 dB amps in the front end, some decent taps, and then your home runs and you're good. That's your entire system design. It's not incredibly complicated. It's not incredibly complex. And I will show kind of examples of this as we go out and when I start to pull drawings here at the end of everything. But that's what you need to know about a home run coax design. Home run coax design, everything's coming back to a single location. All of the calculations that you're doing as far as like how much juice, how much power do I need to get the TV signal to the end of the run is all being done at the front end. It's all being done in that main TR, and then that's it. No amps, no taps, no splitters, no balancing, nothing in line. You just home run. The next one is trunk and tap. trunk and tap is going to be a little bit different. It's going to start with a backbone cable. And that backbone cable is going to go either up the riser or out to the wings and then up the riser, I guess, depending on the building. But everything that you're doing, your TV system is going to come off of that one core feed, your trunk line, which is the backbone of the system. And then in each TR, you put in one of these guys, which is a tap. This one's an 8-port tap. They come in all different types of varieties. I was just using an 8-port for the project that I was working on when I was doing this. So that was the picture that I drew in. And then from there, what you actually do is you just kind of do your home run calculations. So you just treat each TR as you're going up the riser as its own little home run system, and you balance each individual closet. And the question is, well, absolutely, why would I do that when I already have this like home run methodology where I don't have to do any closet by closet balancing? And the answer is really simple, and honestly, it's because some facilities are really big. You're going to see trunk and tap in like a 300, 400, 500 bed hospital. You're going to see trunk and tap in an MDU or like a large enterprise space. MDU, apologies if I over acronym there, is like a multi-dwelling unit. So think like an apartment building or a high rise or something like that. Most of those are going to be this trunk and tap infrastructure because they need to get coax to 1,000 different apartments or 1,500 different apartments across this entire building. You can't home run all of that, right? It's just ludicrous to think about. So you end up with this kind of trunk and tap infrastructure where there's a single hard line going up the backbone, and then you're tapping off in each TR. What we've started to see a lot more of, and really what's a cleaner design from a Z-band standpoint, is a variation of the trunk and tap, which you could call the hybrid fiber coax or HFC system. And I'm going to step outside of the kind of high-rise methodology to think about that. But like think of a college campus, right? We have a head end for your TV systems in an admin building somewhere, and then or in a data center, let's say. But from that data center, we have single mode fiber connections out to each individual building from that standpoint. So what we're going to do is we're going to bring in that feed from the CATV provider. We're going to build that head end, and then we're going to put in a fiber transmitter. And then we're going to take advantage of that single mode fiber that exists from our data center out to each of our buildings across campus and run fiber on the backbone everywhere. And then within each facility, what we're going to end up doing is catching that incoming fiber feed with like a fiber receiver or maybe a Z-band box if this is a Z-band infrastructure, and feeding that back out. And then within that building, maybe we're home run, or maybe there's like a small trunk and tap system within that home run. And then that same concept applies within healthcare facilities. The design that I'm going to end up showing at the end of this was for a healthcare facility that is currently under construction. And they'll be built in the Midwest here. I think occupations like late 2024, early 2025. But that's exactly what they did. You know, there's 40 different TRs throughout this healthcare facility, or like 38, I think maybe the exact number. And you build the head end, you put the fiber transmitter in, you put in your optical splitters, and then each TR is its own home run system, except with the fiber backbone. And the advantage of doing the fiber backbone, just for like full transparency on that, is the fiber backbone is going to give you a cleaner, flatter signal when it hits each telecom room. And there are no like loss and distance calculations the same way there are going to be with the trunk and tap system. The loss per 100 feet on fibers infinitesimal. I think it's like 0.6 dB per 100 feet. So if you launch, at any sort of reasonable level, you can go miles before you have to worry about degrading your signal on a fiber backbone the way that you would on a coax backbone. So that's definitely something that we're starting to see a lot more of. I will pull out a specific design for that in just a few minutes, but this last bullet here, the variation of the trunk and tap system being HFC is something that we definitely spend a little bit of time with. I'm going to switch to laser pointer here so I can highlight that without switching. There you go. So that's what we're talking about right now, the variation of the trunk and tap, which is the hybrid fiber coax system, which we're starting to see a lot more of. the common issue with coax systems, and the reason that like Z-band has had a market since 1999, and the reason that you see IPTV systems and some of that other stuff is I mean, let's be realistic about all of this. From the end user standpoint, TV is TV, whether it's getting there as coax, whether it's getting there through IPTV, whether it's getting there through the Z-band system. You're making those decisions as a system administrator or as a system designer on the back end, because you want to know how easy it is to set it up, and you want to know how easy it is to maintain it and configure it and make changes and that kind of stuff. And that's what's driving your decision for IPTV or RFTV or Z-band. But as far as the end user is concerned, a television is a television. They're watching The Price is Right, whether they're watching The Price is Right as a multicast channel or as a traditional broadcast channel. They don't know and they don't care. It doesn't make a difference to them as long as it's not affecting the quality of the picture. The problem that we have with coax systems is because that's the case, right? Because everyone is already familiar with television from streaming in their house, or setting up their own little TV system when they were a kid, or being the little kid that had to turn the knob on the televisions. Everyone feels comfortable with this, so it's not a big deal for someone to go to Best Buy or Circuit City or Radio Shack or Blockbuster or whatever other extinct store that you want to put in there. Apologies to Best Buy for including them with the extinct stores. But nobody's uncomfortable going and just grabbing 10 feet of coax and a splitter and just kind of making their own television. I had a story from a client that we were with in Indiana. It's a healthcare chain in India that is headquartered in Indianapolis. And we did a switch over, and we're walking down the hallway with our contact at the hospital. This guy comes out of his office. He says, "Hey, what'd you do to my television system?" And our contact there takes out his list. He says, "I don't even have that you ever ordered a TV for us or that we set one up for you." And so the guy kind of gets this like sheepish grin on his face, and it's like, "Well, I just kind of lifted the ceiling panel and found the coax and cut it and did everything myself." And that's more common than you would think. I mean, a lot of the times when we're selling to Air National Guard, Army National Guard, military, one of the common complaints that they have is, and I quote, "The airplane mechanic keeps cutting my TV lines." So you have this thing where, because with the coaxial system, everyone has this level of familiarity with TV and TV distribution, that your end users themselves end up causing problems because they think they can fix it, or they think that they can make an adjustment to the system to give themselves TV, and it's not going to cause problems anywhere else. But as we understand of loss in a system and how we have to overcome loss in a system, even these small changes of a 1x2 splitter or a 1x4 splitter can be catastrophic if the system was already kind of on the edge. So like, once we've decided, hey, we're either going to do an HFC system, or we're going to do a trunk and tap system, or we're going to do a home run system, well, then we have to start doing the calculations for how strong does my signal need to be at the source to get all the way out to the edge, right? And this is the fun part, because it's math, and nobody does math after high school or college, right? You just kind of stop doing it and rely on calculators and the internet. So the first bullet's super important. CATV signal is absolutely never stronger and never better. It's never higher in quality, which is super important, than what it is at that demarc. Every time you amplify that signal, you're going to be reintroducing noise. Every time that you have to manipulate that signal in any way, shape, or form, you're making this like slight degradation to the quality of your TV signal. And that's important to note, because it means that if you're coming in and your signal is like marginal to begin with, and I'll pull up some specifics when we get into the testing equipment. If you're already working with a marginal signal, you're not going to make it to the end point, because every time you introduce that marginal signal to an amplifier, not only are we amplifying the quality, the good stuff within that, but you're also amplifying the noise. So that's definitely something to be aware of, is when we're talking about designing a system, we want to talk about the power that's required to get to the end, but we also want to talk about making sure that that signal quality, which is carrier to noise and analog, and then MER, modulation error rate in digital, we want to make sure that that quality is there too. So on the slide with the meter, I'll make sure to talk through some of those bullet points. The other big thing, and this is where like the math comes in, every time you split a CATV signal, you are introducing loss. So this is I'm going to laser pointer again, coming in 1x2 splitter here. If I'm coming in at 10, each of these legs on the way out are going out at 6.5 because I'm losing 3.5 dB every time I perform this 1x2 split. If I was coming in at 10 and this is a 1x4 splitter, then I'm losing 7 dB. I'm losing 3.5 dB twice, right? And so then I'm down to 3 dB with my output on each of these output legs. So you can see very, very quickly here, I'm about to run into a problem because if I do 10 dB coming in, 1/8, I'm losing 10.5 dB. I'm at negative 0.5 dB at my launch point here before we've accounted for any loss over distance, before we've accounted for any loss over high frequencies, before we've accounted for any potential loss or issues due to poor termination. So, and really what your TVs traditionally are looking to see is, this is going to vary from manufacturer to manufacturer, but a broad range is to say like negative 5 dB up to plus 15 dB. When we design systems as Z-band systems, we're obviously going to operate within a spec if there's a specific spec that we're looking for, but we're always looking for something in the negative 5 to 10 range. I say up to plus 15 as we're doing this webinar because I just recently did a spec where that was the high end of the range that the designer put in there for the makes and models that they were working with. But generally, if you're launching below 0, we have a problem. And this is true for fiber optics as well. So if I'm launching from my fiber optical transmitter at 14 dB and I go through, milliwatts, 14 milliwatts, and I go through a 1/8 splitter and I lose that 10.5, well, then I'm only at 3.5 milliwatts again after we've done that calculation. So you can see when we start to talk about a 100, 200, 500 bed facility, this is exactly why the idea of a home run system or a trunk and tap system is required, is because you're doing so many calculations to get to those 500 drops that you can't just do all of that in a home run system. The amount of like amps and splitters and couplers and everything that would be required in a single head end to support 500 drops and to overcome all of this loss would be ridiculous, which is why trunk and tap is what comes in a later facility or larger facility. So when we're talking about that loss over cabling, this is the other really interesting part about designing a system, is that like most of the coaxial manufacturers are going to call this out in loss per 100 feet. A project that I was working on recently, these were the loss characteristics that they called out. You were able to lose 1.48 dB per 100 feet at 50 megahertz, which is your low end channel 2, channel 3 RF frequencies. And you were able to lose 7.45 dB per 100 feet at 1,000 megahertz, which is where like Comcast right now has some high-end channels. We're also starting to see with like DOCSIS 3.1 and some other stuff rolling out more content coming in up in these range. But this is, if you think of your traditional TV spectrum as channels 2 through 135, which is what it was before kind of like modern cable TV and virtual channels. 1,000 megahertz is up at like above the 135 end of that range. It's a very high RF frequency, and it gets used sometimes. We don't see a ton of broadcasters at this point still using frequencies up that high, unless it's in more of like a residential application. In most commercial applications, you're not going to get up to 1,000 megahertz from the broadcast side of things. You can, it's rare. And then with the RG11 as well, 0.9 dB at 50 megahertz, and then just over 5 dB at 1,000 megahertz. So if we go back to the previous slide in that example of 10 dB coming in, 1/8 split, 0.5 loss coming out, I can't go 100 feet, right? If you go 100 feet on RG6 with that as your loss budget, like you're on the high end, you're not even going to make it the 100 feet until we're out of spec for the television. So this is one of the calculations that you have to make is, do I have RG6 or do I have RG11? I should have some knowledge of where the frequencies are on my head end, my TV system, in order to push those out. If you don't have any knowledge, just kind of aim for the middle, right? A lot of like Spectrum and some other, they're in the 3, 4, 500 megahertz range with their bulk systems. So it's fair to assume that you're somewhere in the middle if you have to do these calculations a little bit blind, or if you're doing a design without really knowing who the service provider is. And that's kind of like roughly what I'll do, and then throw a variance on either end. So you get lost so many different places, right? You have this beautiful signal coming in, it's clean, it's at the right power, and then as soon as you split it, as soon as you put it on a cable, everything gets worse. It gets less powerful, and then you potentially have to amplify, and you have all kinds of issues there. If you could potentially be amplifying noise into your system, if you over amplify, or if there's already a bunch of noise in the system. I don't think I'll touch on it in the next slide. I'll touch on over amplification on the next slide. So the other thing, and I've mentioned it a couple of different times, like I said here, 10 dB coming in, 1x2 split, 6.5 dB coming out. That's how a typical splitter works, right? It's just going to give you this equal loss across every port, and it's defined by the number of splits. Taps work slightly differently, where there's going to be an incoming port, and then there's going to be a straight through port to take you to the next tap in the system, because again, this is designed to feed off of a trunk. That straight through leg is going to have a defined loss, right? Where it's like a dB or two that you're going to drop as you go through the connect and deconnect there in that tap. But then these other 8 ports that you see here are going to have a different loss defined by the value of the tap itself, and not necessarily by the number of splits. It's not algorithmic loss the way that this is. And so you can have 10 dB taps, 20 dB taps. You can have taps with different loss values just based on how the tap is manufactured and put together. So, and there are like some more modern smart taps that give you some adjustability in some of these things. Like this technology's come as far as you can take tap technology, I guess, at this point in time, in the fact that it's like adjustable and manageable and everything. But you see these taps being used because, number one, they're a lot cleaner for mounting things. And then number two, you're not getting that variability of loss the same way you are with a splitter. And so a lot of like your larger enterprise infrastructures, what you're going to get is you're going to get this defined loss here, where you're going to use a tap in and just mount it in the closet rather than using a splitter. And the only like serious difference between the two is what happens here with the loss. You will notice the last bullet, I did say all unused RF ports should be terminated. All RF ports should be terminated. And after having a conversation with one of our electrical engineers last week, if you have the metal RF terminators, those are better and are the better idea for the very specific reason that a lot of those metal terminators actually have a small capacitor in them to help shut off that RF leakage entirely. And it's going to do two things. It's going to save you, obviously, the leakage. And then also, if there is like an amplifier or anything like that within that port, anything that you have tapped, like on the Z-band boxes specifically, the outbound port of a Z-band box is always broadcasting RF. And then as soon as you put that metal cap on there, the capacitor that's in the metal cap actually can shut down the RF outbound on the Z-band side of things. So it's going to limit your ability to damage your own equipment, and it is also limiting your ability to broadcast interference and RF leakage. So you do want to make sure you're using terminators, but we do recommend metal terminators just because they're a little bit better than what you've got here. So now we've done it, right? We have we've decided whether we're going to go trunk and tap, whether we're going to go home run, whether we're hybrid fiber coax. We've done all of the calculations. We've done the loss budget. And so now, now it comes time to actually put the system in and make sure that we did our math correctly. And so as you're doing that, there's just going to be a couple of different tools that you're going to utilize. The one that our engineers tend to utilize, and I'm not telling anybody it's the only RF meter on the market. I'm not telling anybody that it's the best RF meter on the market, but it is the one that our technicians have decided is a good value for us as a cross between cost and function in terms of giving us everything that we want and need when we're in the field without paying 10 grand for a meter. So the device that we use is the Televis H30. The H30 Plus that we've been getting recently does actually have the ability to view channels on the monitor. Or that's not something that's being made up. That's an actual feature of the device. And it's going to allow you to see every channel within your system, the power, and the signal quality. Signal quality is MER. And we did talk about that just a little bit. MER, with a modulation error rate, is basically telling me, what kind of problems I have within that signal. A modulation error rate, a high modulation error rate, means your TV isn't going to be able to pull enough of the good stuff out of the picture, and you're going to end up with pixelization or color bars or like potentially green screen and in blocks and some of that kind of stuff where we can't process the data that's there because of the amount of errors that are in the data. So you just end up with like null data, which is doesn't present well on a TV screen. And so the MER in general, we want to be starting out in like the 40 range or a little higher if you can be. Somewhere in the low to mid 40s is basically perfect MER. And then depending on the quality of your television signal, and then there's some variance with power and everything else like that as well, we want to make sure that we're in the high 30s and can potentially extend down into the mid 30s, even the low 30s with the MER, and still get good signal quality. The issue that you have with digital television is the MER is kind of a cliff, right? You can be at 37 and everything looks great, and then you're at 33 and 34 and you got no picture whatsoever, right? And that line in digital video is super thin. And I like to tell people there are only really three states of digital video. Everything looks great, it's pixelated, I can't see anything. Like, those are the three states of digital video that you have. And we're not used to that, or at least I'm not used to that. I mean, my 40th birthday will be next spring. And so I kind of grew up watching analog television. That was what we had in the house. I was the little kid that had to change the channel on the knob, to change the knob to change the channel every time we needed to watch something different on the TV. And in the analog world, that didn't happen, right? You had fuzz or snow or whatever it is that your family referred to it as growing up. And as that carrier to noise number got worse, as your video quality got a little bit worse, you just got more snow, or maybe it would bleed over into the next channel. You'd have issues like that. It had to be really, really bad or encrypted, scrambled, I guess was the term back then, in order for that signal to disappear. Digital video is not that way. It's far more robust in terms of its transport and forgiveness, but once you cross that line, the TV's just gone. Versus in analog, where you would just kind of get this like continued degradation of the signal until it was just this like snowy mess eventually. So that is worth noting, is like with digital, and it's a dead giveaway when we're troubleshooting clients, is that anytime a client comes to me and says, hey, my TV's fuzzy, that's analog, because digital video is not capable of that. Digital video doesn't do fuzzy. It does pixelated, but not fuzzy. And so that's really what we're looking for in that RF meter. We are looking for not only the power, but the quality. In the RF meter, the Televis H30 or whatever RF meter that you have and utilize is the only place that we're really measuring quality. When we come back to fiber meter, we come back to the fiber meter and we're back to power. We don't have any way to measure quality again. And so this fiber meter is looking for either 1310 or 1550 nanometers. We're simply measuring the power of the optical feed from our head end. And fiber receivers are a little bit different than televisions in that like low and negative numbers aren't bad. I need to change the formatting on my PowerPoint presentation because there actually is a negative sign here. It's just there when I need it down here. So I'll change that after the presentation. But RZHCs, if you're doing a traditional Z-band system, they're looking for at about -2 dB. I was working with some stuff at a VA facility in the Midwest a couple of weeks ago, and they were looking for 0, right? They were looking to have 0 dB coming in terms of the power of the optical laser. So these are great. Fiber meters, not terribly expensive. We can buy decent ones off Amazon for 130, 150 bucks. There are better ones out there depending on the features that you want. But if you just simply want to measure power, you're not going to break the bank to get a meter that looks really similar to this one and allows you to measure optical power. And what do we find? Well, when you're designing a system, your fiber reading should be relatively similar, right? Like if I launch from my head end at 10.5 dB, I go through a 1/8 splitter. I'm at 0 because I just lost 10.5 dB. I should be close to 0 everywhere throughout the system. So if I'm going closet to closet to closet and I'm testing and I get 0, -0.5, -0.5, -5, well, then we have to do further investigation onto this port that's -5, right? Because what happened? Do I have a bad termination? Is there a patch cable or a patch bay somewhere along the line that we don't know about? And there's UPC connection or flat polish connections in there that we didn't realize existed. There are a variety of issues that could cause something like that. But really what you're looking for in a HFC system in that that hybrid fiber coax design is that your values closet to closet to closet should have a small degree of variance because the amount of loss that you're introducing on a fiber backbone is very, very minimal, unless you're running a long way, like thousands of feet or half a mile across campus or something like that. You should not see large variation in your dB levels across different closets in a fiber backbone. And then the last piece here, we have a device, and I'm sure it's the next webinar, just based on kind of the way these things have been stacked. That what it functionally does is called our Signum device, and it's going to be ready to ship in Q1, is it combines several of these functions into one. It is a fiber receiver, can be a fiber receiver. It can be an amplifier with a high output coax. It can be a cable simulator, a signal adjuster. But it's one device that's basically going to soup up the intelligence of your coaxial system and your ability to do RF monitoring and measurement. So we'll definitely touch on that next month with the webinar. But for now, we're just going to cover kind of a traditional amplifier. Traditional amplifier is exactly what you would think it is, where you're plugging coax in, you're going to have an outbound, and then all you're doing is twisting knobs to adjust the slope or the power or the gain of your signal. This is the problem when it comes to designing coax system, and more so than designing coax system, implementing a coax system. And this is why we have the Signum device coming down the line. The majority of our clients, and I would be willing to guess based on my conversations with service providers and other service companies and everything else in the industry, the majority of customers in general don't have any RF meters or any sort of tool to figure out what they're actually adjusting when they're turning these knobs. And so what you end up with is a lot of like what we like to consider to be blind troubleshooting, which is someone's there turning the knobs while someone else is down the hall or in the next room or wherever the problem is on a radio or on a cell phone. And they just stop turning the knobs when the TV works and turns on. And that's great, right? Because you're fixing that issue there. But you also don't know what other issues you may be creating. Are you now overdriving the amplifier and you're introducing a bunch of noise into the system? And we've seen this before. Actually, one of the cases where we had to fight RF leakage as Z-band was where someone had taken one of these feeds. It was a 60 dB amp. They plugged it in, just cranked the thing all the way up, and they were launching at like 75 dB. I don't know. It was some insanely hot number that like the meter didn't even know what to do with. And they were leaking. Like we got a call because the FCC did one of the flyover tests, and they were just radiating RF energy anywhere because they just ramped this thing up as high as they possibly could, and they were just blasting RF. So there is very much an environment here where if you have technicians and engineers who are making adjustments to amplifiers within the system, you don't know what else you're affecting. And if you're doing this without having any tools or anything to be able to give you valuable feedback, this can be really problematic, having people adjust amplifiers and make adjustments to amplifiers without the tools to do it. One of the sales guys around here, we have a saying, you're only as good as the data that you can get, right? And your ability to troubleshoot a coaxial system and your ability to provide any sort of value to your clients in troubleshooting coaxial system is 100% limited by the data that you can collect. And there's absolutely no data that these amplifiers provide back to you other than how far the knob is turned. So you do need to have those meters or access to someone who has those meters when you're doing this. So that's the big potential issue with the amplifier. Not anything that the amplifier itself does, but that the amplifier used in conjunction with someone who does not have the tools to see what they're actually doing with that amp can be pretty problematic. This is actually a little bit longer than I expected it to be, so I'm going to do a real quick show of a design here. And if in order to get ahead of that, if anybody's got questions, any further detail they would like, you guys can start chatting those in now. I will answer questions while I am going through and pulling up this drawing for everybody. All right, so this is a drawing set that we did for a VA facility that it is currently being built. And it is kind of what you expect to see when we're doing a design as Z-band. So I'm going to try and scroll all the way down here to the bottom, see if I can show you guys the fiber part of it first. All right, so the first thing you're going to do, and we're going to do, this one was a complicated head end, just full transparency for everybody. That's not what most of these look like. This is a more complicated system than kind of what we'll traditionally end up doing. Is they had OTA feeds that are coming in, so they want to do local channels. All those local channels are going to feed into a blonder tongue AQT8 for OTA to IP, or not IP, OTA to QAM transcoding. And then the current service provider is DirecTV. So we have DirecTV coming into COM 3000. All of these coax feeds coming into our Signum device, which is what we'll talk about next month, and then into two 26 milliwatt fiber transmitters and two 1x32 couplers to feed each of the 40 plus telecom closets throughout the facility. Hang on just one second. And then once we're out, we are rolling into each of the closets. And then so from the closet by closet basis, we are doing our design for the home run system. So I have my fiber coming in here, single mode fiber from the NCR into the patch bay. We're expecting that input level to be minus 2 dB plus or minus 2 coming into the Signum device. And then we have a 30 dB tap here and a 20 dB tap here. And the reason is all of my runs off this tap are between 100 and 180 feet. So I'm getting less loss here where I'm going up to 235 feet. And that's more extreme in some of the other closets they have where we're going up to 275 feet on the long runs, but only as low as 110 or 130 feet on the short runs. But basically what we are able to do is, because we have a home run from each closet, you just take the length of the run minus what I know my 40 to 45 dB launch level to be, and do the math to make sure we're hitting the receive ends within spec. So there's, on this particular drawing, we have TRs that do everything from just 1 or 2 TVs all the way up to some of the bigger, more complicated ones, which are hosting, I think, 30 plus televisions from a single TR. But this is a lot of what you end up with when we're actually going through and doing these designs and drawings, where we'll go back and we'll do the calculation. And if we're told to, or if it's part of the spec, will all the way out to each room. This one's far more complicated than a traditional Visio drawing, but this is kind of what everything looks like once you put it into practice. We've got our taps included. We have our loss calculations being done. This is a HFC system. A drawing like this is everything that was discussed over the course of the last half an hour put into practice, and this is what you'll end up with when you work with Z-Band on a TV system, where we'll do a Visio design for you and make sure everything is gonna look good. So yeah, that was a lot. I apologize that this is a little longer than ours have traditionally been. I think one of the things that I like to hit on, and kind of what I'll end with here, is not everyone, that's unfair. There are a lot of folks within the industry and a lot of folks that I talk to just kind of in life who think that TV is easy, right? And they believe that TV is easy because everybody's got TV at home and TV at home works. Or you have TV in the hotel when you go travel and that works. And I get that. I understand like the mentality behind that and why you would believe that from like a framing standpoint. But the truth of the matter is, when we're talking about in corporate environments, enterprise environments, TV is actually still kind of complicated. There are a lot of loss values and calculations and conversations about head end and that kind of stuff that need to go into actually adequately designing a television system. So like the next time that you have a project or you're working on a project on the TV side of things, the only thing that I can ask is like, please don't leave TV till the very last thing that you do, and start making phone calls about who your service provider is and how you're going to do TV 2 months before the system goes live. It's just not enough time to do it. The world of television has changed enough over the last 5 to 10 years that it is a slightly more complicated process, not necessarily because of coax design and everything else like that, but like some of the other conversations we've had this year, where once you started adding in encryption and content security and everything else, TV takes time and it takes a little bit of thought and planning, and we're happy to be here to help with that. And I will shut up for a minute or two and let you guys type in questions if you have them. Everybody should have a toolbar, and if you just want to use either the chat feature there, you can chat me a question. I'm going to use the Q&A feature. We can do a Q&A question, and if not, I'll give it a minute or two here, and then I will sign off with one last apology again to anybody that I kicked off at the beginning of this presentation. That was completely an accident, so apologies for that. Yeah, I will give it a minute. All right, thanks everybody. I don't see anything in terms of chat questions, Q&A questions. Appreciate all of the time that you've spent with me today and this year, and we'll see you again next month to talk about Signum. Thanks everyone. Bye.